Perfect. Yeah, welcome. Welcome to our talk, Practical Data Science, How to Track Your Development Process with DVC. And I would say let's get started. Yeah, we already talked about us. Let's start with our project. So we want to show you a little live example. And the perfect example is basically an automated checkout process in supermarkets. So imagine you are buying some fruits, and how does it work? You have to weight the fruit, the cashier has to put in the numbers, and you have to pay. So wouldn't it be awesome if the cashier just weights the fruit, the machine detects what kind of fruit you are buying, like a banana or some strawberry, and already can bill you and you can pay automatically. So that's our idea. And we want to build a model that can classify fruits. And how would you start? So how did we start in the early days when data science wasn't as common as it is right now? We would build our model interactively. And we start with exploring the data, and everything is happening in Jupyter Notebooks. So Jupyter Notebooks are quite common. We've heard them a lot of speakers talked about them right now. And yeah, let's start here. So we check a little bit. Okay, our image is just 100 times 100. It's from a data set that we got from Kaggle. This is just, we say, all right, we have batches of 32 images. Let's go over it pretty quickly because the interesting part comes a little bit later. We need train data, we need test data, and we load everything in our Jupyter Notebook right now, and we want to start training a classifier. And let's have a short look how our data set looks like. We have bananas, we have lemons. Our data set is pretty balanced, which is a good sign. Yeah, overall we have 982 images, and this is just how it goes in the normal workflow. Probably every data scientist knows it. Load the data, look a little bit into the data, how does it look, how it is balanced, all interactively to see how your model might behave. And we also can look a little bit at the images. Oh, bananas and lemons, but anyway. Yeah, this is how it looks. So we see, oh cool, all the images are quite clean, it might be easy to train, so simple task. There's not much noise in it. And we say, wow, this is an easy task to solve. We can even solve it on our machine without big computation power. So we create the model with Keras. All right. Overall, we can go through the model pretty quickly. So this is not about the data science, pure data science. This is more about how can we integrate this part, what we are doing right here now in our development process. But let's have a short look. So we are using a famous convolutional neural network. We have a convolutional layer, which is detecting features on the image automatically. We are using a pooling. Pooling just helps us to drill down the features and reduce a little bit the dimensions to make training faster. In the end, we use simple dense layers, which is basically a feed-forward neural network that helps us to classify what is this. Okay, that's a really simple neural network that we are using. And now we train it. Let's see how it works out. Pretty quick. So if we see right here, I mean, our example model is totally overfitting, and it's probably even too big and too good for this simple task. But that's the first idea. I mean, we get some good results. We do it interactively, and we see, yeah, our hypothesis that we can detect if there is what kind of fruit we got, a banana or strawberry, works quite well. Okay, we do an evaluation. And we see, oh, not the best part, but it suits us enough right now. Well, this is really not the best thing. Anyways, this is the process how we would go on now. We have a quite a bad model, and we need to make it better on the test data. And let's assume this evaluation was quite well, and we are happy with our results. Now we go back from the data science approach, and we start being software developers, data engineers, whoever. Because this is what happens most of the time in bigger companies or in organizations. You had this project to analyze something, to bring up new features. It has to be something with AI, something with machine learning because it's fancy. And the hypothesis was proven, and now it says, yeah, worked in Jupyter, we are done. So now it's a problem of operations, DevOps, whomever. And yeah, that brings some problems with it, because how do they know how to operate machine learning models? What does it mean? And then we have to think, well, what does production mean? What does deployment in production mean? Probably all the software engineers right here in this room, they already know that. But what about the data scientists, or junior data scientists, or junior software engineers? And production has a lot of different facets and dimensions that you have to take care about. And there are some famous papers from Google. I can really recommend them. It's What's Your ML Test Score? And Hidden Technical Debt for Machine Learning Systems. Both from Google, and basically these points, they are copycatted from these papers. Maybe some points are added by Tim and me. And it shows a little bit, so where do we take care about? So we have different clusters, as you see. So there's the data test cluster, so data class, regression test, integration test, unit test. So a lot of stuff that you really know from software development, proper unit testing and integration testing, as well as regression. But interestingly, there's also data tests. And if you look a little bit into the news, TensorFlow Extended is really getting famous. And in TensorFlow Extended, there are all these tests like model validation, dataset validation, test dataset validation, with training dataset validation, and so on. But we have more. We need proper logging, monitoring, alerting, and then maybe rescheduling, so scheduling for trainings for machine learning models, because machine learning models live. It's not like you deploy your model and you are done. No, it's like code, right? It lives, it has bugs, it has problems, it has to be changed. It has to be changed often. We need data aggregation and processing. So we already assume that now we do some pre-processing. Maybe we do a binarization on the images. We just make them black or white. What does it mean in production? We need the same code. So there's also code in there. And yeah, for us, for today, the most important ones, our training has to be reproducible. Our models have to be versioned. And if we go back just here, here's nothing reproducible. It was an experiment that we did. We might deploy it to production. If there's a bug and someone was already working again on that Jupyter notebook, he doesn't know what kind of hyperparameters were used, what images were in the data set, why is it behaving on such image. So here's nothing reproducible and nothing is versioned. It's just a model that came out that we might be pushing into production by hand. And there's also automation, CI, continuous integration, continuous deployments. And all these aspects that we see here, they are pretty common in software development. So, what are the arising problems? One problem is models, data sets, they are binary, they are more often they are really large. And the first thing that we have is we need to find a proper way to also track models, data sets, binary files, whatever, in a proper way. Git will get into its boundaries. There's Git large file system, which works well. There's DVC, what we talked about today. That's one part. So a good thing is if you can basically get your model, push it into the cloud, and push your data set into the cloud. That's one part that DVC also helps you a lot. And there's a bit more. Now we talk about engineering, software engineering, data engineering. And as we see here, we have our experiment, right? The interesting part is we also have our application, and we have a deployment. And the whole data science experiment, the workflow, it's always a little bit decoupled from the pure software engineering. But interestingly, the pre-processing code has to be used, We need this code. I mean, there are ways to integrate them, different ways. We can talk about this. And also there's the model. And the most important thing is the pre-processing code has to comply to the model that you use. I really liked a talk from yesterday, machine learning engineering. I have to reference it because there was a great way to version and have basically a definition what version, major, minor, patch is used for what change. For example, well, we change the inputs, or well, we do some tweaks within, or we change the model. That was great. I can really recommend to listen to this, because this is exactly what applies here. So, and yeah, with these problems, we need a good stack. Probably a stack for data-centric applications that help us to make all these things easier, so to dive a little bit easier into software engineering practices when we do data science and experiments. And what we've noticed is, well, Python sneaks more and more into enterprises. So with Docker, containerization, heterogeneous systems, Python is not a problem anymore for any operations part or any operations business unit or division. And since Python is really, really helpful for data science tasks, it sneaks more into the corporation and be used also in production systems. Well, TensorFlow Keras works really well. With TensorFlow 2, it's really intuitive. You can start quickly. This is one part. You could also take PyTorch, whatsoever. But this is the stack that really helps us, at least at Codecentric and on the customer side, to use or implement these systems. We have DVC, data version control. Tim will talk way more about that later. That helps manage large files and also manage the reproducibility and versionization, or versioning. And we have TensorFlow serving for inference, which helps us to simply serve our models and provide them as a REST service, REST endpoint, or gRPC. And I would like to hand over to Tim.
Yes, at this stage, I'd like to take over, and I'd like to talk about what Mark already mentioned about these parts of production readiness, which are reproducibility and which are version control for our data and our models. And I would like to show this by using DVC, which is a really neat tool which we basically found in the internet and thought, hey, let's have a look at that. And so you might ask yourself, well, why do I need that? I mean, I have version control for my code. I have Git, or SVN if you still use that. Why do I need that for my data, for my models? And the answer is reproducibility. Mark West said it yesterday in his keynote. Data science is hypothesis-driven, which means we need to conduct experiments. We need to have a look at our roadmap, at what there is to be done in order to improve our models. So you probably have in your Jira backlog, you have things like, oh, I need to check out my hyperparameters, maybe even do some hyperparameter optimization. I want to check out principal component analysis or some kind of feature engineering. I want to add new layers to my models or remove them because they've proven to be useless. And so you end up with lots of experiments, with lots of models that you build, and at some point you get easily lost in being actually able to say, okay, this model, these experiments have been performed with this exact setting. And the same holds for the data. You probably don't have this simple Titanic data set when you work in production, which is beautifully crafted for you. But you have some heterogeneous data which come from multiple input sources. So you might have some sensoric data. You might have different databases which you connect to each other. And over time, data sources become available, or they get lost because sensors are getting damaged. And so you end up with multiple data sets, and at this stage you're just not able anymore to know exactly which data version, which binary did I use for that, which CSV, together with which code that I wrote to create which experimental results. And the other reason why we need reproducibility is collaboration. I mean, you usually don't work on your own, do you, in your team? You have multiple roles, as Mark also said in his keynote yesterday. You have this data engineer, data scientist, and so on. And they are all distributed probably by now. So you may have colleagues in Vilnius, or in Berlin, or in Madrid, or in Paris, or in San Francisco with which you work in a team. And when you performed some experiment and you want to show the results and want to give the model to your colleagues, you don't just want to give them your model code, because training takes 4 hours, 8 hours maybe, or you push up your CPU resources, your GPU resources. So this might really become a bottleneck. And this is something where version control really comes in handy, because you cannot only give your colleague the model code, but also the trained model. And this is where data version control comes to the rescue, can help you tracking this development process. And so what it does is something very similar to Git large file storage. I don't know, does anyone know Git large file storage or has used it by any chance, or Git Annex? Okay, 1 or 2 people at least, that's cool. So the idea is totally the same. You have your normal Git repository, GitLab, GitHub, whatever, which you interact normally with your code. But additionally, you also have a second remote storage, which is an S3 bucket, or a Google Cloud storage, or your local NAS server, whatever. And this one is responsible for syncing your binary files. And so this coupling between binaries and your code happens by creating metadata files in your Git. So for each binary that you want to track, you automatically create a metadata file which contains the name, the location, and most importantly, the hash sum, such that it exactly knows if a binary has changed over time. If the hash sum is still the same, cool, nothing to be updated. If the hash sum has changed, all right, I need to update this and sync it again. And since the metadata file is very small, and it's textual, it's a YAML file, you can just commit it together with your Git code. And what DVC also does for you is the ability to automate this process by creating pipelines. So by now, you most probably also know that it's really easy and really useful to create machine learning pipelines, which consist of preprocessing, training, evaluation, deployment, validation, whatever there is to be done. And DVC allows you to optimize your reproducibility by creating such pipelines. And so you define stages with it, which have 3 properties, namely the dependencies, so what does a certain stage rely on, and based on which it figures out whether a stage has to be reproduced. Some process itself, so most probably your R script, your Python script, your shell script, could be really anything. And some kind of output artifacts, so DVC knows what's going to be the result of your stage. And you connect those stages then naturally to a pipeline. So this is, a really typical pipeline that you could use here. So this is so much for DVC and the theoretical background before we can get hands-on, because I would like to get hands-on with you. Just a very quick refresher of TF serving if you haven't used it before. TF serving is a lightweight model server that comes now with TensorFlow Extended, was also there with TF1 something, and works in a very easy way. So you're, as a data scientist, work on your Jupyter notebook, you're happy with the result, looks really cool. So you deploy it, which means you basically copy it to TensorFlow serving, and TF serving then manages all the models that have been uploaded. So if, on the other hand, you have your checkout machines, or 1,000 checkout machines, or 1,000,000 checkout machines, they can simply ask for inference. So you put your banana on your counter, and it basically just asks TF serving, what's that? All right, so much for that. So let's get into it. We want to develop now the fruit classifier. We've seen the first part, but now in the proper way, which means we're still using TensorFlow Keras, but we're versioning it now with DVC and having a continuous delivery in cooperation from DVC and TF serving. And since I don't have a self-checkout with me in my back pocket because it's really hard to get it through border customs, I will try to simulate that with my webcam. So let's get to it. We're still in the area of version control, so we have to initialize our version control. We can't skip that part. If you're familiar with Jupyter notebooks, you might notice the syntax. You can execute shell commands in a Jupyter notebook by prepending an exclamation mark. So we just start by git init naturally, and also start initializing our DVC repository by DVC init. And here you can even see that DVC comes really natural to use if you're already familiar with Git, because it shares lots of commands. And so it feels very simple to get into it because you already know the Git syntax. And so it gives us some information that it's collecting now usage analytics, which is not, because I'm not connected to the internet, but in theory it is. And now we also need, after our initialization, to also add remote storages, right? So for Git, this would be probably some link to your GitHub repo or wherever it is. For now, it suffices to just use some temporary folder here. And equivalently, we add our DVC remote storage also in our temporary folder. So this is where the large binaries will be stored at automatically later on in our process, such that we can use it for collaboration. So if Mark wanted to sync his laptop with my findings, then he would just connect it to his DVC remote, and it would be automatically getting synced. So this has worked, and now we want to create our data pipeline. It consists of 3 steps. A loading step, which is some kind of pre-processing, so I have my data source and some configuration file, and these go into my loading step and create some kind of pre-processed data. Then I have some training, which creates me my trained model, and then I have my deployment stage, which allows me for continuous deployment up to TF serving. So let's get right into it. Now, my grocery store that I want to help out is really small. It only has 2 fruits. It has banana and strawberries because it wants to check out whether these suffice for customers. So I say, okay, for now, my classifier should be only able to classify those 2. And so I write that in some kind of configuration file. And then I ask DVC for creating such stage, my preprocessing stage, which I will name loaddata.dvc, and then I define the dependencies and the output of this stage. So the dependencies are the shell script that is doing the preprocessing. It is depending on my original data source, which I downloaded from GitHub, and is dependent on this very much fruit.txt configuration file. And the output will be some data folder. And the processing that actually happens during this step will be the load data script. Meaning that when I ask DVC later for reproduction, it will check the hash sums of the dependencies and will be able to figure out whether this stage is still up to date or not. So this has been done. This is really quick, and it asked me to also add it to my version control system. So that's what I'm doing right now. This is the normal Git terminology, which you're probably familiar with. So I add my shell script and my metadata file, give it a commit name and push it, and also ask DVC to sync my data folder up to my remote storage. And this has been done already. It doesn't look very beautiful because I'm in a notebook, but it's done. All right, let's quickly go over the next two stages, which is the training stage, right? So I will call it train.dvc, and it depends on the data that I've just created. It depends on my Python script that is training the model, and it will output me 2 things. One, a saved model, which I can give to TF serving later, and a version file. And then executing is Python fruit detector.py, and of course I again do my version control stuff, add, commit, push. And this is training on my model, so it has created my metadata file and is executing my script. It's again 5 epochs. It's the same model that you've seen before, so it's really not very good. It's highly overfitted, but that's all right for us. And it is uploading my model right now to my remote storage, so this is very nice. And of course, I have a third stage, which is my deployment stage. It depends on my deployment script, on the model that I just saved, and the version file, and does some deployment. So this one does not have any output. This is also very quick, because it's just moving it to a location where TF serving can pick it up. TF serving is already running in the background with me. This is all very nice. All right, so we've created our 3 stages. technically, our pipeline is ready. Well, let's have a look at that. And as you can see, this is what DVC has recognized. So we only defined our stages independent from each other, but DVC has seen that there are some relations between it. Some dependencies, some outputs relate to each other. And so DVC knows exactly which stages have to be performed in which order. This is very simple, as you can see, but in theory it could be any directed acyclic graphs if you have more complex pipelines. So what about our live prediction? I told you I will try to do this actually with you. So let me start my webcam. I don't have fruits with me, but I have something like that. I have a picture of a banana. I hope that is all right for you guys. And my webcam started in the background, so I'm a strawberry. That's kind of cool, I guess, because I'm red. And if I try to put a banana up, okay, I got a banana. Strawberry, banana. Nice. But now my grocery store wants to extend. Now it didn't only get strawberries and bananas, but it also got walnuts. And walnuts really doesn't fit my model right now. I mean, I can start it again. I shouldn't have closed it. If I ask my webcam, my self-checkout machine to classify a walnut, it will say it's a banana. Or what does it say? It's a banana, which it isn't. So I need to, as a data scientist, I need to get hands-on again and need to update it, my model. And this is where DVC shines because I can just ask DVC for reproduction. So if I would do it now without any further changes, it would just tell me, oh, yeah, there's nothing to be done. Because there is nothing to be done. I didn't change anything. But if I now say, okay, DVC, this configuration file that I had in the beginning also tells me that I want to classify walnuts, and then ask for reproduction, then it will detect that a dependency of my very first stage has changed. And so it will also provide me in my data set images of walnuts. And then it tells me, oh yeah, you know, my data has changed, I need to retrain my model again. So it does that for me automatically, which obviously takes a couple of seconds. And when my model has trained, I also ask basically DVC for deployment, and that's exactly what it tells me. My deployment stage has changed because there's some change in my dependencies in the models. And so it also redid the deployment. So if I now ask my webcam for a classification of a walnut, hopefully it will be able to, but we're being live here, so don't expect too much. Well, it's kind of straddling between strawberry and walnut. I guess it's fair enough. It's a bit difficult. Theirs are not too similar, though. All right. We tried, though, and in theory, my self-checkout machine is being able to classify walnuts by now. So much for the live example. This has been very basic, obviously. There's more to DVC, which I cannot show you due to the lack of time. Like you can track metrics if you want to. You can see how the accuracy, your F1 score, your kappa score evolves over time. You can have some cross-interaction between your projects. You can import artifacts from other projects if you're keen to. You have support for all the big cloud providers, AWS, Azure, Google Cloud Platform, whatever, local machines. If you want to do it on-prem, that's all cool. You can do some more advanced remote caching, but don't do it because it's not worth it, but you could do it, and even more things. And now if you ask yourself, that all sounds very nice, but does it also cover my use case, which is a bit different? Well, honestly, it depends, which is the standard software development answer, because there's obviously always advantages, disadvantages. But that's okay because there's alternatives to it. Like DVC is not the best at experiment tracking, for example, like showing the evolution over your metrics. It's maybe not the optimal tool to. But that's all right because there's tools like Sacred or MLflow or all the other ones. And you should really try it out. If you see, okay, vision control for data is really cool, but DVC doesn't seem to fit my case, check out the other ones. So there's a really cool awesome list on GitHub. You should check it out if you haven't already, where all these different tools are displayed. All right. To have a short recap.
Yes, let's do a short recap. So overall, I mean, we've heard it now for the whole conference. Changing the role model for data scientists is heavily changing. Data science algorithms, machine learning algorithms and models, they get really accessible and easily accessible for everyone, which doesn't mean data scientists are not needed, but there is also a big need for data engineers. Well, better is a combination, a data all-star, who knows about experiments, who knows the math behind, who can do exploratory analysis and find interesting facts in the data. But data scientists should also be able to deploy his model into a production environment, to know a little bit about software development processes, how to work together in a software development project and environment. So that's because the trend goes from one-off analysis to data-centric applications. The one-off analysis is one part, it's the proof of concept. It shows that your hypothesis works, but the actual value after it is not your presentation in the end. The actual value that you need is the application that is using your model. So that's the important part. And that makes machine learning models first-class citizens in data science, in data-centric applications. It's like configuration, it's like code. Well, it's configuration and code. So you have to take care about machine learning models and about the cycle of also experiments in order to have an application really use machine learning models in the end. And I personally think this is a big change. And well, DVC really helps you to use this. I mean, Tim has shown you a lot. We've missed out a little bit about versioning, but the versioning and releasing works the same like you use tags in Git. You can have your own like version pattern or versioning pattern. DVC helps you with reproducibility. We've seen this, but DVC also helps you to simply take the deployment script and run this in a build server for a certain release. So the integration with Git is really perfect, and we would be happy to talk later about how it also works with your whole release and deployment process in the end to provide continuous integration, continuous deployment for data-centric applications and for machine learning models. And this is what we've seen here.
Yes. So thanks a lot for listening to us. And if there are any questions, we're now happy to answer any of them.
Yeah, thank you, Mark and Tim.